Hey everybody, I just wanted to run through the reading notes and make sure that you feel kind of comfortable with the questions that I had you answer and that you know what it's all about. So I want to just kind of run through and make sure that we summarize. Now, I really strongly recommend doing the reading and summarizing this on your own, but it's nice to kind of have this as a check to make sure that you did it properly. So first, in dealing with electric charge and electric forces, we should just sort of give a brief overview of what it is that we're talking about. So we've studied a number of forces in IB physics, including pushes, pulls, tensions, and there's one special or different, distinct kind of force that we studied that is able to act without touching or having contact with any object whatsoever. And that force, of course, is the gravitational force. And again, we've studied that force, we've used it, we've dealt with it, we've done calculations with it. And there's a couple properties about this force that actually do make it a good springboard to talk about the force we're going to discuss today, which is the electric force. So one thing about gravity is that if you notice, it acts over a distance, and the other thing is that it really affects masses. So just to kind of distinguish that from what you read about the electric force, what we found is that with electric forces, the thing that carries that force, or that generates that force, if you will, is a property of matter called charge. And so what I want to do is just a quick distinction between the two forces, even before I answer the questions. So first, with the gravity force, if I had to distinguish, it affects mass. And as far as mass goes, there's only one kind of mass. And that means gravity is always attractive for us in this universe, as far as we know. Now, we may later discover that there's some other type of mass that's a negative mass and it makes gravity repulsive. But as far as we can tell, gravity is always attractive. And I want to contrast that with the electric force. And basically, it affects, or rather, it is caused by something called a charge. Or rather, it affects, and I'm going to say gravity is caused by mass. Here it's caused by something called charge. And with electric forces, there's a difference between electricity and gravity in that there are two kinds of charge. We've got positive and negative. And what we have is that like charges repel and opposites attract. Now, the thing about both gravity and electric force is that both forces in the math, when you look at the equations for the forces, both forces have 1 over d, the distance squared, in their equations. Okay, and so you'll hear these called 1 over r squared force laws by physics nerds everywhere. So now we're ready to kind of go a little bit deeper here. And I actually, know what, before I do that, I'm just going to write out here. So the gravity force that we studied is Fg is g, which is a constant, times the mass of one object times the mass of a second object divided by the distance between them squared. And for the electric force, what we have is that the electric force is equal to a number k, q1, q2, which are the charges over the distance squared. So similar math, but there are a couple distinctions in how they act. So the two assumptions we make about electric charge, the first assumption we make is that electric charge is conserved. It's not created or destroyed. And the second assumption we make is that charge is what we call quantized, and that means there is a smallest possible charge, and every charge is a multiple of that. Okay, so we actually have like little tiny bits of charge that sort of pile up and add together to make up every charge that we see. Now, it turns out electrons, we discovered later on, are negatively charged. And there is an experiment that was done to show that, but we're not going to worry about that too much in this class. Now, when we say that charge is quantized, what we mean is that it comes, so it comes in little, what we'll call discrete hunks. And what I mean by discrete is there is a smallest possible charge that can't be broken down further. And when we say charge is conserved, again, what that means is charge is neither created nor destroyed. Whoa, that looks really nice. Charge is neither created nor destroyed. And that's the idea. Okay. Now, this is the equation that we use to calculate forces between charges. And just to be clear, what I like to picture is I like to picture one little charge Q1 here, and let's put another positive charge Q2 here. Now, we said like charges repel, so what that means is we'll have these two forces pushing each charge away from the other. And the force that we're talking about here is exactly this force here. Now, there is a small little thing, this little epsilon naught. I want to talk about this. So this number k, it can actually be broken down into another weirder number, 1 over 4 pi epsilon naught. This is really useful in advanced physics, and we discuss it briefly in IB. And it turns out that this little constant here is called the permittivity of vacuum. It kind of tells you, it's kind of the default strength of the electric force. And you'll actually find out that real materials have different permittivities that reduce the strength of the electric force in most cases. So, for example, here it says the electric permittivity of graphite is 12 times that of vacuum. So let me just kind of be clear. Here's Coulomb's law, F equals K, Q1, Q2 over the distance squared. That's just the force between two charges. Now here's what we're saying. If the permittivity of graphite, and let's just work the equation. So it turns out when you have permittivity in your equation, you want to rewrite K, this constant, using this formula here. Now just to review, this constant K, it's in the data booklet. It's a way of kind of getting you the strength of electric forces. It's just a constant you put into these problems, kind of like G is 9.8. Well, K is 9.9 or 8.99 newtons meters squared coulombs to the -2. So when we actually put numbers into this formula, all we're saying is this. This is the normal force, or not, sorry, this is the regular force that we deal with. And then what we're saying is, instead of epsilon naught, we're saying that the electric permittivity is 12 times that of vacuum. So we're going to have 12 times epsilon naught here. And we have K. We're told the charges stay the same. Whoops, sorry, no K anymore. Q1, Q2. And we're told that the distance doubles. So what we do is we actually pull out these factors, just those factors, to see how the force is affected. And so what we realize is that the force is actually 1/48 as strong. Okay. And again, just reviewing those assumptions about electric charges, they're quantized and it's discrete. Now, the idea of the electric field basically is it's kind of a factoring trick. Here's the force law for two charges. And here's what we're going to say. we're going to gather this little term here and say, hey, we're going to pretend that basically Q1 makes this invisible thing that reaches out to grab Q2. So if Q1's here and Q2 is here, we're kind of saying that, hey, why don't we just say that Q1 puts this thing out into space that affects the charges around it, and we'll actually call it the electric field. And then Q2 feels it. And it actually turns out this little silly factoring trick is a real thing. It's sort of like we said, hey, let's just factor this because we're not really sure how Q1 can grab Q2. We'll just pretend that there's this invisible thing there. And then it turns out that it really exists. That's sort of how I find it useful to think of it as a student. The history is a little bit more complicated than that, but I think as a student, it's a really good idea to kind of think of it that way, that, hey, we're going to factor this, and it turns out that that's not just a little factoring trick, it's actually a thing. So it's sort of like, hey, F is KQ1 over R squared, and then I times it by Q, and all of a sudden, oh my goodness, this thing here is actually a real thing that we call the electric field. And then the last topic that we cover is this notion of electric current, and it basically says here that the electric current is basically the charge passing through a point per time. And so just to kind of review, delta Q is the charge that passes through a point, and delta T is the time it takes for the charge to pass through that point. I is what we call the electric current. And you know what? I don't like my writing here, so I'm just going to clean it up a little bit. So the idea here is that delta Q is the charge, is the time elapsed. And then what we can actually talk about here is this notion of I being the electric current. And by the way, the units of electric current are amperes, and it turns out that coulombs, the unit for charge, are actually amperes times seconds. Now, this letter N is it's basically the number of carriers per unit volume. It's a density, okay? A is the area of the wire you're sending current through. V is the speed of that, of the charges, and Q is basically, as usual, charge. And what we're basically saying is the picture here is that we have a wire, and we've got this area here that the charge passes through, and we're basically kind of calculating, so this is the area, and what we're basically saying is that we have this charge, whoops, that's not what I wanted to do. So here's our area, here's our wire, and we have this big mess of charge just passing through. It's got a certain speed, and we're saying the area times the speed times the density of the charge tells you the current. So we're kind of thinking this as sort of a fluid, and this is the formula for calculating the bulk amount of current that's just flowing through a wire. So that's kind of this, and then we have just one last little thing here. So for example, here it says estimate the drift speed. Once again, there's not a lot we can kind of do here. We've got a density, we've got radius, we've got this kind of stuff. And the other thing that we want to be clear on is the charge on an electron is 1.6 times 10 to the negative 19th coulombs. This is given in the data booklet. So the kind of problem we're dealing with is, hey, look, I've got some electric current, and I want to figure out the density, meaning the number of electrons per unit volume. So we want to get the drift speed, actually. We want to figure out how fast the average speed of the electron. So basically, we're going to say it's NAVQ. And there's not a lot to do here. We've basically got 1 amp of current. We're told that we have 10 to the 28th. So the density here is 10 to the 28th meters cubed. The area here, now this is a wire with a radius 2 millimeters, that's going to be pi. Now let's convert that millimeters, 0.002 squared. What are we doing here? This is the area of a circle. So we got 1 times Q, and that's the charge of an electron, 1.6 times 10 to the negative 19th. And V is the speed that we're actually solving for here. So basically, what we have is this number here that we can go ahead and calculate. I will actually do that right now. And I'm getting 4.9 times 10 to the negative 6th meters per second. So it goes really slowly, but there's so many of them, that's how we generate a current. Now, let's just kind of be clear on something. If you recall, the work on an object is the force times the distance. Now, one thing that we said was when we go back to Coulomb's law, the electric force on an object, yeah, it's K, Q, Q over R squared, Q1, Q2 over R squared. But if you remember, we factored out this part and we called it the electric field. Let me just modify this equation just a little bit. So the work done on a charge is actually equal to Q times the electric field times the distance you move through. And what we're going to do is we're actually going to, just as we talk about this invisible electric field, it turns out we can kind of talk about a potential energy field that permeates all of space. And we call that the potential difference. And it works like this. So we're going to take work and divide it by Q, and that's the electric field times the distance you travel through. So the potential difference is basically the work per unit charge. And I really don't like this because it's really more of a math thing, but it ends up being useful later on. And so it's just a formula that we have, but we'll actually use it in problems in a little bit. And then the electron volt is a unit of energy that's equal to 1.6 times 10 to the negative 19th joules. This is useful for energy of electrons, protons. It's an energy unit, and subatomic particles, which we'll get to in our last unit. So this right here is basically 1 electron volt. So that's kind of a quick summary of the reading that we've done. And basically this is the essential information. We'll use it to look at some problems in a minute.